Hello there, top of the morning to you. Actually, it's pretty late. It's 11:04. Um, we're gonna continue our walkthrough of the LLVM tutorial. We're in we're at the end of chapter 2. Last time we were gonna finish, but we ran up against some compiler problems, compilation errors, I should say, and wasn't able to get to the finish line. But I did a little bit of research offline, and I figured out how to move forward. So I'll share that with you. So last time when I was trying to compile the program, I think I was doing it like, let's see. First, I was compiling it just like this, even without these flags. So I was compiling it like g++ mylang.cc, and then output mylang.bin. And when I did that, I ran up against a lot of compiler errors. When I followed the tutorial suggestion to use these LLVM config to generate the flags, then that got a lot better. Actually, at this point, everything is fixed. So those flags are kind of important. We can look through those flags to see what they actually did. But anyway, now I still had an error, which was caused by me forgetting to use the standard move function to move this argument, so sort of grant the ownership of this argument to this vector, I believe. So previously I had the code like this. I think, and I got this error, which I actually showed this in the previous video, where I only had one single error left, and I was reading through this ginormous error and I got confused. And then I tried to compile their code as is from the tutorial, because at the end of the part 2 they actually have a full listing of the code. Actually, this is their code from part 3. I later on wanted to test part 3, test compiling their code from part 3, just make sure we wouldn't run into a hurdle like we did last time. But anyway, I tried to compile their code from part 2 and I still had trouble. But eventually I figured that out as well. But anyway, I'm gonna stick with my version of the code. And the only thing that was needed to fix this error was to add in this move, to make sure, that the sort of ownership of this arg was granted to the vector that contained it. And now this compiles, and that is pretty important. And after the thing compiles, what you get is a program that is sort of like a REPL. It's for JavaScripters, that is like the developer console. You can type in code within this language, for example, and you have to end the line with a semicolon. That's how it works. So like 1+1, and it says I parse a top-level expert. If you want to define a function kind of looks like this. Maybe like, I don't know, fib of n is fib of n minus 1 plus fib of n minus 2, semicolon. And it actually was successful in parsing a function definition. If I had a syntax error in there somewhere, I don't know, I had too many parentheses or something, I'll just do n+1. Then I get a parse error. Okay, so this all makes sense. Let's try an extern. Do we support variable assignments like that? Unknown token when expecting an expression. I don't actually think we support variable assignments at this moment, but we do support function definitions and numbers. Like that. Okay. Does that work? Okay. So anyway, we have this parser working from part 2, and that is great. Before we move on to chapter 3, let's look a little bit at what these flags coming from the LLVM config is. I want to check my audio. Make sure. Hello? Can you hear me? Yeah, I think the audio is good. Okay, he's using my Yeti mic. Because one time I recorded this thing and I had my microphone set wrong, and then the whole video had no audio in it. And I didn't want that to happen again. Okay. So, why don't we just copy this line out? This line that says LLVM config with the CXX flags and execute them on their own. So LLVM config -- CXX flags, and you'll see these flags for the G++ compiler. I actually think I have G++ aliased to Clang++. So it's probably in reality using Clang. This I flag is saying add the include file, add the header files within this include directory to the list of header files to use. This is saying use the C++ 14 standard, which probably comes with a bunch of syntax features that the code within the tutorial uses. I actually don't think at this point we're using any of the includes from this directory, so it's more likely that there's a bunch of these things here: std constant macros and std format macros. I don't actually know what those things are. Maybe they are stuff that's defined in this include directory. I don't actually know, but in any case, these are, and this is no exceptions. I guess we want to turn off exceptions from C++ or something. I don't know what all these flags are. I just wanted to show you that there's some special flags that LLVM has configured for projects using it. Even though at this point we have written a parser that doesn't actually depend on LLVM just yet, but we will. Last time I talked about this, but I want to say again, which is that in the getting started guide for LLVM, which is in a different part of the, let me go there. And I did their getting started guide a long time ago. The getting started with the LLVM system, I followed this tutorial, and what they recommend, the way they recommend you get started is clone their repository and then go in there and build LLVM from source. When I tried it last week, I had lots of problem with it. It was running this compile job and it seemed never to end. So finally I gave up. And maybe if anybody is watching that knows how to compile LLVM correctly or more efficiently, please let me know, because I would like to do this. Anyway, I punted, and instead of trying to build LLVM from scratch, I downloaded the binary instead. So I went to LLVM home, and I went to this available for download link. And I downloaded a binary. I went for the latest version, which is from March 24th. And then I said download, and I grabbed the pre-built binary for Mac OS, which is the operating system. And as you can see, LLVM supports all these different types of architectures. And that's all various combinations of operating system versus CPU architecture. And that is pretty cool. So that's how I have LLVM installed. And once I extracted the compressed file that was in this download, I then extracted it and put it in a subdirectory inside my home directory. I called it lang-LLVM because that's the content within it. It contains LLVM core as well as Clang. which is the C compiler. And then within this subdirectory, there's bin, which contains the LL compiler, as well as other tools from the LLVM suite. Yeah, let's display. So all of these tools are coming from the LLVM suite that I can use from the command line, and I added this to my path in my startup login file. And as you can see, there's also lib. The include directory contains various headers, and then the lib directory contains various pre-built binaries for various parts of the library. Okay, so this is how I got it set up. You can set it up the same way, or you could maybe try your hand at compiling LLVM yourself. Anyway, we're gonna move on to part 3, or I should say chapter 3, which is quite exciting for me because that's actually a new area for me now. Yeah, so let's get into it. We have built a parser which is able to take some source code and generate an AST tree. The next step is to write some code that traverses the AST, the abstract syntax tree, and generates code in the LLVM IR format. So we're gonna generate some LLVM IR code, but we're gonna generate this code with the help of a library, a builder library that is provided for us by LLVM, which will make this process easier. I don't know exactly how much easier. And also, I have taken their code from the end of chapter 3 and compiled it to verify that I know how to compile it. So hopefully we won't run into the same hurdle we ran into last time. Yeah, so I created this build file, which will compile both my code and their code. Oh, I found that when I tried to build the code the prescribed way, I got this weird error that says like it's a LD, which is the loader. It's an LD error that said it didn't understand one of the options that was supplied to it. And that was because the loader that I have on my computer is older than the one that the LLVM used to compile itself. And if you have that situation, what you do is you tell Clang the version of your linker using this flag, which is what I did. I figured out the version of my loader by doing LD with a version flag. It tells me the version of my loader, and then I just informed the Clang++ compiler, hey, my linker's version is that, so don't try to give it anything that it doesn't understand. So anyway, I got this build script. I'll probably use it to do stuff, but I'm gonna comment out this line and probably will use it later. So now I'm gonna start out on chapter 3. Let's see how far we got. Okay, I'm gonna do it slower because this is a new area for me, and also there's gonna be a lot of stuff to cover. So welcome to chapter 3 of implementing a language with LLVM tutorial. We have already, this chapter will show you how to transform these abstract syntax tree, which we built in chapter 2, into a LLVM IR. This will teach you a little bit about how LLVM does things, as well as demonstrate how easy it is to use. It's much more work to build a lexer and parser than it is to generate LLVM IR code. Smiley face. That's actually a little bit hard to believe at this point in my knowledge level, but that's also good to hear from someone. Please note, the code in this chapter and later requires LLVM 3.7 or later. Well, I did download the latest one. I actually downloaded version 10.0.0. That's the one I downloaded, which is way later than 3.7. Holy crap, how old is this tutorial? I'm really happy that it still works, even though the tutorial is like 7 versions behind. Also, well, it works so far. We'll see. Also, note that you need to use a version of this tutorial that matches your LLVM release. If you're using an official LLVM release, use the version of the documentation included with your release or on the LLVM.org releases page. Oh, really? Okay. Are you saying you have multiple versions of this tutorial? But this is like the like master version of the tutorial, isn't it? Is there like, oh, documentation, okay. Oh, I should put like this flag in front of here? Is that what you're saying? No, that doesn't work. Okay. Intro to getting started. Let me try that. Table of contents. We're within the 10.10. Okay, so you're saying I should use this version of the tutorial with a 10.00 in front of it, but it's still gonna say requires 3.7 or later, which is fine. Okay, so I should be using this version of the tutorial. I have a feeling though that the master version is probably the current with the latest version of it. I'm gonna stick with this master version that's on the website. And yeah. Okay, so in order to generate LLVM IR, we want some simple setup to get started. First, we define virtual code generation, CodeGen methods in each AST class. So remember how initially when we created this expert AST class, this one, we had, come on. Computer is kind of like sluggish on me. We had this virtual expert AST destructor, but now we're going to add another virtual method on it. Actually, not crazy about doing it this way, but again, the tutorial did say this is not necessarily the best practice way of doing this. So, you know, I'm taking it with a grain of salt, but I'm gonna follow along. So we're gonna add a virtual method to the base class, which requires every subclass to also implement this method. What the heck is this equals 0, by the way? That's a very specific C++ syntax, actually. That is saying this virtual method has no implementation, is not implemented, and also it's required that a subclass must implement this. This equals 0 is how you specify that. I find that really weird. That's how they designed it in C++. Let's just go with it and not criticize. Now, so given that every subclass, including number expert AST, variable expert ASP, etc., has to implement, like, give a real implementation of this method. What is this value thing? We might need to import a header in order to get what value is, I think. Yeah. Value is the class used to represent a static single assignment SSA register, or a SSA value in LLVM. I think I'll have to talk about SSA shortly. Let's go ahead and do that, actually. And perhaps I'll do that. I'll talk about SSA, and then I'll cut this video short. and then we'll continue in the next one. Okay, what the heck is SSA? Honestly, I am not very knowledgeable about it, but what I do know, based on reading this Wikipedia page, I would say that, first of all, the design of SSA is very, very central to the design of LLVM. All of LLVM, there's a lot of architecture within LLVM that is based on SSA, which stands for static single assignment form. And the reason static single assignment form is desirable, and probably the reason why LLVM chose it, is because if you have your program written in SSA form, it makes possible a bunch of code optimizations, which are listed here. So constant propagation, value range propagation, sparse conditional constant propagation, dead code elimination, global value numbering, register allocation. That's a particularly interesting one for me. I don't understand what every one of these are, but I guess a way to summarize it is to say SSA form is a valuable thing to have, because if you have your program in this form, then you can benefit from all of these types of compiler optimizations, which are all of these compiler optimizations are well known and well researched, and there are good implementations for them, good algorithms for them. Which is all to say that helps your code get faster at the end. So that's why LLVM has chose to center its architecture around SSA. What the heck is SSA? SSA is saying, you know what? It's a sort of like a rule. If you have an arbitrary piece of program, such like this one, you have this program. That's not in SSA form, because in order for a program to be in valid SSA form, it requires that every single variable you have in the program can only be assigned to one time. So every var can only be assigned once. Exclamation point. And therefore, if you wanted to translate this program into static single assignment form, it should look like this. Instead of assigning to y 2 separate times, we actually are going to need to name a new y, call it y2. We have y1 and y2, and then we only have one x, so that's x1. So this program in SSA form is converted to this. Now, why is this valuable? Well, there's some algorithms for figuring out that code, right? Clearly this first line is completely useless because the second line is gonna override whatever it does. So the first line is like dead code. We should optimize that away. That should just go away. That doesn't need to go into the code at all. So an optimizer can come along, sort of go through the AST that represents this code and realize that that line of code is completely unnecessary. We're going to strip it away from the final resulting program. That kind of algorithm is harder to do when the program is in this form. But if you convert it to SSA form, that kind of analysis is much more easy and efficient to do. That kind of analysis includes all of these things. Like that code elimination is one of them, but all of these things are algorithms that are easier and more efficient if the input is already in this SSA form. So that is, in a nutshell, at a high level, what SSA is, and all of the code that we generate in LLVM IR will be in SSA form. We're gonna see that. So with that, I'm gonna stop this video at this point, and then in the next video we'll actually start implementing some of the code in chapter 3.